So we're on page 27. These are the discussion questions from chapter 2. And we can read them together. I think we're going to do all of them. So start with number 1. It says, can an object have 0 velocity and still be accelerating? Erica, this one's for you. What do you think?
The velocity, no, it's the slope of the velocity is the acceleration. So,
Okay, so can you ever have a slope of 0 on a velocity graph? Velocity graphs can never have 0 slope?
I don't think so.
Yeah, the only thing...
Like an instant, I mean.
The only thing we said was like typically acceleration graphs are like the step functions, but anything about velocity like that. And typically we are dealing with no? Okay. Typically we're dealing with constant acceleration, so you would have constant slope. Perhaps that is what you are thinking of, but we don't have to have a constant acceleration, and we could certainly have, you know, something like that, where the slope is 0. In which case it's got 0 velocity and it's still accelerating. Or, okay, even other than having a slope, I'm reading the question wrong. Sorry. Can it have 0 velocity and still be accelerating? That would be slope of position. I apologize. But yeah, that is certainly possible. Or if you're thinking of a velocity graph, can I have acceleration and velocity end up at 0? You know, sure. Perfect example is just a projectile. You've thrown something up. Maybe it stopped for an instant at the peak. That entire time, the acceleration that was affecting it was gravity. So yes, you can have 0 velocity and a constant acceleration. All right, Daniel, part B. Can an object have constant velocity and still have a varying speed? What was the definition of velocity? As a vector, what did it mean? What were the 2 components of velocity in the vector definition? It had a blank and a blank. Okay, it had a magnitude. The magnitude is the speed part of it. And then it had a direction. So it could be 50 miles an hour left, right, up, down, whatever. That makes it velocity. So can it have a constant velocity, for example, 50 miles per hour to the right, and still have a varying speed? No. No, it's just a definition. It's kind of like the square is a rectangle, but rectangle's not a square thing. So no. Velocity is a combination of speed and direction, so if the speed's changing, the velocity is changing. All right, C. Zach. Can the velocity of an object reverse direction when the object's acceleration is constant? For example, gravity.
Like if you throw it in the air again.
Perfect. Yes, if you throw it in the air. It will definitely be reversing direction, but it is a constant acceleration. It's just at the beginning, the velocity and acceleration didn't match in signs. Velocity was positive, acceleration was negative, so it was slowing down in the beginning and then speeding up after it reversed directions. All right, Wes, can an object be increasing in speed as its acceleration decreases? So this one's kind of tricky.
Yes.
Yes. Care to elaborate?
If its acceleration decreases, it can still have some acceleration. It's going faster.
Good. It didn't say its acceleration went from like positive to negative. It just says there's less acceleration. So an example would be like flooring it, like slamming on the gas pedal, and then letting off a little bit. You're still gassing your car, you're still accelerating, just at a slower rate than you were before. So you can continue to increase in speed as your acceleration changes. You just would be increasing in speed less quickly. I don't want to use the word slowly, but you wouldn't be speeding up as quickly as you were speeding up the first time. All right, number 2. This one is looking at the graph on the page to the right. Tyler. All right, so we have a graph of particles' position along an x-axis versus time. A, at time t equals 0, what's the sign of the particle's position? Positive, negative, or 0? What? Negative. Good. And don't be tripped up by like easy questions like this. You'll often have a graph and be asked about either that graph or like velocity or acceleration. Just remember how to convert between the two. But this is a position graph. It was a question about position, so it's clearly in the negative down there. All right, how about the velocities, the particle's velocity at 1 second, 2 seconds, or 3 seconds? Is it positive, negative, or 0? Marcella, what do you think for 1 second? What? How do you get velocity from a position graph? Okay. Distance over time, displacement over time, which on this graph would be slope, y over x, rise over run. So it is a positive slope at 1 second. Keep going, Marcella. How about 2?
0.
Good, 0. No slope at 2, and then 3, negative. All right, and then Connor, how many times does a particle go through the point x equals 0? X equals 0 is the x-axis.
What's this axis?
Yeah, that's what's confusing.
Okay, sorry.
So the actual x-axis.
Maybe I should, the actual x-axis
Yeah.
with the time, so 2, okay. Where x equals 0, you have 2 times for that spot. Okay. All right, number 3. Okay, not that graph. All right, Emily. All right, there's a little bit of a setup here. All right, number 3. At t equals 0, a particle moving along an x-axis is at position negative 20. Wake up. Okay. Okay, so we're just starting there. The signs of the particle's initial velocity and constant acceleration are for 4 situations. Either positive, 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 negative, negative, positive, or negative, negative. Okay, so we'll think about that. So those are signs for velocity and acceleration. In which situation will the particle A undergo a momentary stop? Draw. What do they tell us? Okay, so this is positive, positive. What was the next one? Okay. Before I get Emily to answer the question she already answered, let's just make a quick guess at the graphs as to what they would look like. So they're position graphs, so the slope is dictated by velocity, and whether it gets more steep or more shallow is dictated by whether it matches acceleration. So if I have a positive slope for this first part and a positive acceleration, what would that look like? Yeah, getting steeper, something like this. Down here.
positive shallow.
It goes like this. Okay.
Yeah, it's getting more shallow. Maybe there, maybe later. This one?
It's going down. Shallow down.
Down, but getting more shallow. This one.
Down.
Down is big.
Okay, so those are our 4 graphs. And all right, back to Emily's question. Which one, again, given enough time, would you have a momentary stop? So you said which ones?
What would be if it changes in direction?
Yeah.
So it'd be the first one. Because it's going from negative to positive.
So its position, its position is going from negative to positive. So, to the left of the tree, left of the tree, left of the tree, at the tree, to the right of the tree. What?
I don't see how any of them. I don't know. I don't understand.
Okay, well, remember this is what our slope was positive, and if we have a negative acceleration, like we didn't match, that meant the graph got more shallow. So that always meant that we were doing what? Speeding up or slowing down?
Eventually go.
Slowing down. Now, given enough time,
Stop and go back.
this acceleration will win out and change the direction of the velocity
To the negative.
to the negative. So the only cases where that's possible would be 2 and 3. Okay, and again, definitely pass through the origin. Brandon, what do you think? Now, my drawings may be misleading, but definitely pass through the origin would be only one answer.
The positive.
Yeah, definitely this one. Which other one maybe?
Negative, positive.
Yeah, this one here, because I don't really know where it's going to stop in reverse directions. Maybe it stops in the negative position region, maybe it doesn't.
Would the negative positive ever turn around the numbers?
Huh.
I lied to you. Given enough time, you're right. It's not just one. Given enough time, that's going to happen over here. Thank you, Brandon.
And on back to 1 and 1 and 3.
So 1 and 3. Come on. Come on. And definitely not pass through the origin. That one's only 1.
That one's
Yeah, negative, negative, definitely not headed towards the origin. Okay, good job on that one. Thank you for the help, Brandon. All right, number 4. All right, another graph. All right, the figure below gives the velocity of a particle moving on an x-axis. What are A, the initial, and B, the final directions of travel? Does the particle momentarily stop? Well, let's start with Thomas. What's the initial direction of travel?
Are you like positive or negative or like
Yeah.
positive? You're like where it is?
Well,
Where it's going.
what can you tell me about the sign of velocity in the beginning? It's negative. So again, imagine you had your tree. In the beginning, if it's a negative velocity, you are moving away from the tree. Now, does the velocity get more negative? No. But does that mean it's headed at the tree? If I'm the tree, either way. Slower and slower and slower. So it is negative initially. Now, in the final direction of travel, the line ends up in what? direction. That's just directions of travel. That does not mean I've even made it back to the tree at all. I don't know where my reference point is. Does the particle momentarily stop, Thomas? Would velocity now, again, you get asked this question a lot. Is it a slope question? Do I just look at the graph? What do I do? If I'm asking about velocity and it is a velocity graph, you're just looking, does it ever cross, v equals 0? Yeah, so velocity, would be 0. I'll pick on, all right, back to Erica. Is the acceleration positive or negative?
Acceleration constantly positive.
Good, and how do you know?
Because
Because it's a slope. And you said constant, which is correct because it's, it's not curved, it's a set slope. The slope is always the same at any instant in time. So that graph might be showing, again, on the tree, something's moving to the left of the tree. Direction, and now it's coming at the tree faster and faster and faster. And that's pretty much all it's telling you. All right, number 5, Daniel. All right, initial and final velocities respectively of a particle in 4 situations are all of that mess. The magnitude of the particle's constant acceleration is the same in all 4 situations. Rank the situations according to the magnitude of the particle's displacement, greatest first, during the change from initial to final velocity. Okay, now, the discussion questions, are not intending for you to grab your calculator to figure these out. Usually you can figure them out without, at least hopefully. So Daniel, looking at the problem, what information is given about this particle?
Final and initial velocity.
Okay, so we know final velocity and initial. Just leave it like that. What else does it say is the same? So it has a constant what for all of them?
Meters per second.
Keep reading. Those are all the velocities. It says the magnitude of the particle's constant acceleration is the same in all situations. So I know given initial and final velocities, I know the acceleration, and what's the question asking for?
You want to rank them?
I want the actual term we're trying to find.
Displacement.
Displacement. Okay, so pause. So that's given stuff, that's the question. Daniel, what kinematic has got all that stuff in it?
V squared equals V squared plus 2a alpha.
Yep. Okay. So you want to solve for delta x. You would have to use that equation given what you're given. Now, so we think, all right, this is going to be a tedious problem. I've got to plug in every single one of these values. But look at, let's see. It says it's the initial and final velocities respectively. What's the initial velocity in A, Daniel?
2.
What about B?
-2.
C?
-2.
D?
2.
Okay, so what's going to happen when you put that in here? Is it going to be different for A, B, C, or D?
No.
No, because it's either 2 or -2, and you're squaring it. What about over here, squaring it again? So all the finals were 3 or -3. So which one's going to have the greatest displacement, or are they all going to be the same?
They're all going to be the same.
They're all going to be the same. Even though you have positive and negative signs, you're squaring them, so they're all the same. When you end up solving for delta x, it would all be the same. All right, number 6. This one is going to Zach. Number 6 says the following equations give the velocity of a particle in 4 situations. All those expressions. To which of these situations do the equations of table 2.1 apply? That means the kinematics. And first question, Zach, do you remember what our rule was to use the kinematics? Yeah, you could only use the kinematics, and it said it in a lot of your homework problems, or they were just using gravity. If what's constant? Yes, if the acceleration is constant, then the kinematics are fair game. So the question is, in which case is the acceleration constant? So Zach, how do you get acceleration from a velocity function? You do the derivative. All right, so go ahead, Zach. What's the derivative of a there? V equals 3. 0. So, is 0 a constant? Yeah, I mean, it's an acceleration of nothing, but it is constant. So you technically could use the kinematics there, although you would just get kind of right back to example. Like if acceleration was 0, and your initial final would be the same, which of course would make sense if there was no acceleration. But you kind of end up there. This is this formula you can use when velocity is constant, but you cannot use that when you have acceleration. Anyway, all right, let's keep going. B. What's the derivative of 4t squared? 8t. All right, so automatically you have t involved. That's not constant. How about C? What's the derivative of 3t? What's the derivative of negative 4? All right, so C is good. C is constant. You could use the kinematics there. And then lastly, D. What's the derivative of 5t squared? Okay, so again, not constant. Wes, back to you. All right, number 7. Suppose a hot air balloonist drops an apple over the side while the balloon is accelerating upward at 4 meters per second squared during liftoff. A. What is the apple's acceleration once it has been released? What do you think, Wes? At the exact instant. Or the instant after that. Okay, common guess, but no. And when we study Newton's laws and forces, acceleration comes from a force. So if there's some upward and some buoyant force, lifting, that would be causing that acceleration upwards of 4. But as soon as you let it go, does that balloon have anything to do with the apple anymore? No. Now, that balloon probably affected its initial velocity, sure. When you let it go, perhaps it is going up for a moment. So the balloon may have affected its initial velocity, but as soon as the balloon is no longer involved, the acceleration would have to just be what? Negative 9.81 meters per second squared. So it would just be gravity for A. Although I guess I probably answered your next question there. If the velocity of the balloon is 2 meters per second upward at the instant of release, oh no, I didn't. What's the acceleration then? Okay, well again, it's gravity. What's the apple's velocity just then? Don't make this harder than it is. What do you think, Wes? The velocity of the balloon is 2 meters per second upward at the instant of release. What's the apple's velocity at that instant? And this time I'm asking for velocity, not acceleration. There you go, 2 meters per second upward. It would immediately start to slow down, but that's it. All right, 8. Back to Tyler. All right, you got a graph Y, so position, velocity, and acceleration versus time for a cream tangerine. Told you there were sometimes some interesting objects they picked. What is a cream? I don't even know. I mean, I know what a tangerine is, but a cream tangerine?
Like a mushed tangerine.
I don't know. Okay, anyway, that is thrown straight up from a cliff, but which upon falling back down barely passes the edge of the cliff. And then we're also going to draw them if it was dropped and not thrown up. Okay, so we have a cliff. Essentially, that's what's happening. Let's do acceleration first. As soon as you let it go, like your hand is no longer involved in accelerating it so that it's going to move upward, what's the acceleration do, or what's the acceleration, wait, Tyler, on the green tangerine? Does it ever change? No, okay, so. There you go. All right, I don't know, which one do you want to do next? Okay, position. Well, I've kind of drawn it for you. I guess it should be Y, sorry. So we're starting here at the reference point, goes up, back to the reference point. Of course, time is going on now. In the actual picture, just be straight up and down. But as time is going on, this is what's happening. And then it passes the reference point. Keeps going below the cliff. All right, how about velocity? Start positive.
Goes through 0.
Tell me about the slope of that graph, too. Is it getting steeper, more shallow, constant? It's constant. You were right. So it passes through 0. And where would it pass through 0? At the peak. All right, perfect. So that's our graph of the cream tangerine. If I had just dropped it, how would the graph look different? Would the acceleration one change? No. Here, we would just start at 0 and it would be getting faster and faster in the negative direction. And this one would be missing this whole part of it. And this should be getting steeper and steeper and steeper. It is getting faster and faster and faster. But my drawing maybe didn't show that. Okay, we're gonna make it, maybe. All right, 9 short. Marcella, you throw a ball straight up from a cliff, from the edge of a cliff, and it lands on the ground below the cliff. If you had instead thrown the ball from the cliff edge with the same speed, I feel like I missed a word. Would the ball's speed just before landing be larger than, smaller than, or the same as previously? So, back to Tyler's problem. Somebody throws a cream tangerine straight up, someone throws it straight down. This one would obviously take longer to get to the ground, but when they get to the ground, would they hit at the same speed, or would one be greater than the other?
One will be greater.
Which one?
The one that was thrown up.
The one that was thrown up, because it's had more time to gain more speed? Hold on. What if I made the cliff the cutoff? What's happening to its velocity as it goes up? It's decreasing. What is it right at the peak? 0. What happens as it falls back down? Increases. But we said this before, projectiles are symmetrical. So when I get back to the same height, back to the ground level or the cliff level, You know, if I threw it up at 40 miles an hour, when it gets back here, it's also what? 4 miles an hour just going down. So it will take longer, but it's only just gotten back to the same speed that this one was thrown down at to begin with. So it would be the same. Oh, 10's a nice one too. Who lucks out with 10? Connor. Okay, we kind of talked about this one too. The driver of a blue car moving at a speed of 60 miles an hour suddenly realizes that he's about to rear-end a red car moving at a speed of 40 miles an hour. To avoid a collision, what's the maximum speed the blue car can have as it reaches the red car? Just don't say 0.
That's 40 miles per hour.
Yeah, 40. As long as it's going 40, by the time it meets the other car, it won't hit it. All right, I'm going to skip 11 for just a second, come back to 11. Number 12, you have a particle moving along an x-axis undergoes 3 periods of acceleration. This is acceleration graph. Rank them according to the increases they produce in the particle's velocity greatest first. So Emily, back to you. How do you get velocity from an acceleration graph?
The area under the curve.
Area under the curve. So which area is the greatest?
Are we like doing total or just for each section?
For each section.
1 and 2 are the same.
Yeah. What are 1 and 2? 8? 7, yeah. So 1 and 2 actually would be the same, but that last segment from 9 to 10 would be less, would be 7. So that's just area, just a reminder. We hadn't had an area question yet. 13, second ball is dropped from a cliff 1 second after a first ball was dropped. As both fall, does the distance between them increase, decrease, or stay the same? Your guess might be to say that the interval stays the same, but it doesn't. Because after 1 second goes by, you'd want to use like the same displacement formula to figure out, you know, the next displacement. And even though 1 second's gone by, they won't keep the same distance increment because they have one variable that's now very different. If I wanted to find out the next displacement for the next second, you know, okay, so if this goes from here to here, obviously this was the first displacement, and after the next second, the second object would also go from there to there. But does this object go equal or more after another second? It goes more because it's already accelerated, and now its initial speed for the second segment like is something. It's not dropped, it is something. So it's going to keep increasing that interval. Okay, so the bell rang on us earlier and I didn't get to finish up question 11. So I thought I would do that real quick right now. Do it the old-fashioned way. But here is question 11, one of the discussion questions from chapter 2. It says, at t equals 0 and x equals 0, an initially stationary blue car begins to accelerate at the constant rate of 2 meters per second squared in the positive x direction. So the blue car had the head start. At 2 seconds, a red car traveling in an adjacent lane and in the same direction passes x equals 0 with a speed of 8 meters per second and a constant acceleration of 3 meters per second squared. What pair of simultaneous equations should be solved to find when the red car passes the blue car? Okay, so the blue car has a head start, but the red car has a greater acceleration, so it will eventually overcome the blue car, and at some point down the road, you know, they will overlap. So the question is asking to solve for time. When will they overlap? Like so. But we don't really have enough information from either car individually. We only know really 2 variables from either car separately, but we can relate them and then find our time when they'll meet. What we do know about the 2 cars that relates these 2 scenarios is that eventually down the road they will meet and they will have traveled the same displacement. So the blue displacement and the red displacement will eventually be the same thing, and that's what we can set equal to each other. But we need a nice kinematic equation that involves all of these variables. So I'll switch to black for that. So looking at what we have initial velocities, and obviously both cars will be speeding up. We have their accelerations, and we know that their displacements will eventually be equal, and we want to include time somehow. We don't know what time is, but we want to find that. So an equation that would be useful here would be this displacement equation. And I can set that equal for red and blue. So I can set this equal for the red card and for the blue card. So for the red car, our initial velocity was 8 meters per second when it passed x equals 0. Don't know what time is. We'll leave that as t. Acceleration for the red car was 3. And again, we don't know what t is. We're going to leave that as t. Set that equal to blue information. Where v naught is 0, that part will actually go away. And we'll have 1/2 the acceleration, which is 2. But here's the one sticking point. They actually have not been traveling for the same time. So I cannot just simply call time for the red car the same time as the time for the blue car. And the blue car was the car that had the head start. So the blue car has been traveling for a longer period of time. It said it had a 2-second head start. So whatever we are calling time for the red car, which would just be t, we've got to realize that the blue car has been doing that plus an additional 2 seconds. So that's one of the tricky parts of this problem. Don't forget to include the plus 2 seconds there. Or, equally valid, you could simply call the blue time's time t and the red car's time t minus 2, since they've been traveling for 2 less seconds. Either way, this is the equation you would have to set up to solve for time. The end.